Okay, we are trying to graph some key points for polynomial functions. So we're learning about graphing with polynomial functions, and specifically we're learning about how to identify the zeros of the function. So the zeros of the functions are the points at which the function intersects the x-axis, also called our x-intercepts. The polynomial function of degree n can have at most n real zeros. What that means is that if it's a second degree polynomial, like a quadratic, the most x-intercepts, or the most number of times that it can cross the x-axis, would be 2. So a third degree can have 3 real zeros, fourth degree could have 4, fifth degree could have 5 real at the most. Okay, it could have fewer than that, but that's at the most. An even degree polynomial has an even number of zeros, or it could have no zeros if it doesn't touch the x-axis. An odd degree polynomial will always have at least 1 zero and then an odd number. But this is kind of interesting because sometimes you'll really see that this isn't always holding up true, but it basically, we'll have to discuss this as we get into this concept of complex zeros, or the multiplicity of the zeros, how often the same zero gets used. So we'll have to expand on these concepts as we learn about how the zeros work. Okay, now for the first problem, it says graph each function and identify the zeros. Here I suggest you go to Desmos and you type in y equals x cubed plus x squared minus 2x. And on Desmos, what I want you to do is find the x-intercepts. And you're going to find that they're at -2, 0, and at 0, 0, and at 1, 0. And so we'll plot those points. And I'm going to let my scale go by, I'm going to let each 2 tick marks equal 1 unit, just to give myself a little more space here. Like this. And the same with my y-axis. And I'm able to do this because I've already graphed this, and I really know where these things are going to land. Okay, so we've got our x-intercepts at -2, so we'll put a point there, at 0, 0, and at 1, 0. Next thing we'll do is we'll look at our Desmos graph and find our y-intercept. Well, guess what? It's also at 0, 0. So these are our key points, or key features. Turning points are the points where the graph goes up and comes back down. And so there's some turning points there. And the turning points given on Desmos are at -1.2. So you can only, Desmos gives to the third decimal place, but just go ahead to the 10th spot. So -1.2, and then for y is, oh, sorry, this doesn't make sense. The x value, I'm going to give myself a little more space here. The x value is -1.2. The y value is +2.1. So that's one of our turning points, and that's right about here. So we're just going to estimating where that's going to be, maybe a little higher. And then the second turning point is at 0.6, say, approximately, and -0.6. Okay, so at 0.6 and -0.6. Okay, so these are our 5 key points. And we can see from the graph that the function is kind of crossing through. It's going up to this turning point, down to that turning point, and it's heading down, down, down here, and up, up, up here. We call that our end behavior. What are the arrows doing, right? So where are the arrows going? So all of our key points are identified here. We show them on the graph, and that's how we sketch it. So our zeros, by the way, are all of the x values at the intercept. So the zeros are -2, 0, and 1. Okay, now do the same thing for this quartic function, or fourth degree. Okay, and so this one, when you go to Desmos and you graph it, which I'm going to do right now, we see that our zeros, right? So our zeros, our x-intercepts, seem to be at -1 and at 1 and at 3. So we'll plot those points, -1, 1, and 3. Not the 2 here. Let me just clean that up. Okay. So -1, 1, and 3, those are our zeros. We see turning points up at around -0.4 and 1, 2, 3, 4. And also at about 2.3 or 2.4, something like that, and 4. And so our end behavior seems to be coming up. It's pretty steep. We're going up through here to this turning point, down, up, and down. And so these ups and downs are increasing. So the function is increasing up to the first turning point, decreasing down to this turning point, which is also one of our zeros, increasing again, and then decreasing. Our end behavior, we can see that these are going down towards -infinity for y as x gets larger and larger. But these are all the key points we want to show, and then we want to show those arrows as our end behavior. Oh, by the way, what was our y-intercept? I think that was given there too. Our key feature for our y-intercept looks like it's at 0, 3. Did I hit that point? No, not very well. Let me try that again. Okay, so we want to show that other key point on our graph. And so we want the zeros, we want the y-intercept, and we want our turning points. And again, we're using Desmos to really help us find all those key points. Okay, but what we want to be able to do is we want to find our zeros without Desmos. We want to try to use factoring to help us with this, okay? And the graphs and the factors and the x-intercepts and the zeros, those are all very much related. So let's talk about that. So linear factors of a polynomial reveal the zeros. Linear factors can be found by writing a polynomial in factored form. And typically what we also do is factor out any a value. But here the a value is 1, so we don't have to think about that for this problem. So for this problem, to factor this, we look for our GCF, which is x. And then we're going to have x squared minus 2x minus 15. We'll go ahead and factor that quadratic. Two numbers that multiply to -15 but add to -2 should be -5 and +3. So if this is our function in factored form, that's what this is, factored form. By the way, we were given standard form. And we're asked, what are the zeros? So the zeros are going to be whenever any one of these factors equals 0. So if x equals 0, or if x equals 5, or if x equals -3. Those are going to be our zeros. Now, if you're doing this, by the way, and you don't have this ability to print this, you know, if you can just jot down these sentences, jot down the function, sketch your graph, jot down the function, sketch your graph, and then go ahead and write down this problem, show the factored form, and write down the zeros, you're going to be all set. Okay, similarly, for our next page, we'll do the same thing. Here we're going to talk about multiplicity. So that's our vocabulary word, very new, multiplicity. So the multiplicity of a zero is equal to the number of times its corresponding linear factor occurs. So on this particular problem, there were 3 different linear factors. None of them were used more than once. They were all just used one time. However, in this function, see the way that this graph, this point, see how the graph crosses through here, and then it touches here, and then it crosses here. This was used once, this was used once, but this one, because it doesn't cross, we know that this one was used twice. So these have a multiplicity of 1. This has a multiplicity of 2. So let's get into that. We'll do that by example. So let's go ahead and factor this. So we're going to factor out the x. We're going to have x squared minus 6x plus 9. This looks like a binomial, x minus 3 times x minus 3, but let's factor that out. We're going to think of two numbers that multiply to positive 9, but add to negative 6, and we see minus 3 and minus 3. So we see that x minus 3 is used 2 times. So this typically we would write like this. To do our simplified factored form is going to look like this. And the zeros are just going to be, again, if any factor equals 0, so that's going to be x, if x is 0, or if x equals 3, or if x equals 3 again. And so we're not using that. We're not going to, it's the same number, so we don't need to really list it twice, except to really show that it is being used twice. And so the zeros are going to be 0 with a multiplicity of 1 and 3 with a multiplicity of 2. Okay? And here, I'll put little colons here so it doesn't look like 0 minus. Okay. Now, if we want to graph that function, this is how the multiplicity affects the graph. Basically, we're going to plot our two zeros at 0 and 3, and I'm just going to do single spaces here, 0 and 3. That's going to be the two places where the graph touches the x-axis. And remember, if the multiplicity is odd, then the graph crosses at that 0, and if the multiplicity is even, then the graph sometimes it's called bounces or touches. It's going to touch at that 0. Okay, so let's get ourselves some other key values here. Let's think about where's our graph going to be here. We could go to Desmos, but let's try graphing this without Desmos. This is a cubic function. A cubic function generally looks like this. That's the parent function, y equals x cubed. And we want to mimic this end behavior, meaning that in quadrant 3, our function should be going down to negative infinity for y, and in quadrant 1, our function should be going up to positive infinity for y. So that's what we're talking about when we talk about, like, what's the basic shape. But it's going to come through, it's going to cross through at 0, and then it's going to touch down at this number. So it's going to be doing something like this, and something like this. That's our basic shape. It's going to touch there and cross through there. Now the thing we don't really know is how high this point is. So we would need a little help to figure out that point, the value of that turning point. So we could use some algebra, we could do some guess and check, plug in some values until we can find it, or again, turn to Desmos to help us find an accurate turning point. But this point right here is not totally accurate. Okay, but let's just practice now some of the identifying the zeros and stating their multiplicities and describing the effect on the graph. Okay, so we can see that for this particular function, we are going to have a 0 at negative 7. The multiplicity is going to be 2. We can tell from that exponent there. And the effect of that multiplicity is that it's going to touch at that point, or bounce, okay? It's going to touch and go back the way it came. It's not going to cross the x-axis. This one, what's our 0 here? Well, maybe we need to do a little algebra here. This is going to equal 0 if 2x equals negative 1, which would mean x would have to equal negative 1/2. So at negative 1/2, we'll have a 0. The multiplicity, again, looking at that exponent, an invisible 1 there, multiplicity is 1, so it's going to cross through there. It's going to cross when x is 1/2. Okay, and then the last one here, this factor will equal 0 if x is 4. The multiplicity there is 3. That's an odd number, right? So we have an even, we have an odd, and we have another odd. that's where it's going to, again, cross at those points. So that's going to be the effect on the graph. So this is the 0. We look at the value of the factor. What would set that factor equal to 0? Multiplicity, we look at how many times that factor is used, and that exponent tells us what the multiplicity is. And then the effect, again, we look at it and say, is it even? It's going to touch. If it's odd, it's going to cross. Okay, cross through, like here it crosses, but at 3 it touches because the multiplicity on that was 2, even. Okay, let's do another one. This one, it's hard to say. We need to put this into factored form. So we'll look for our GCF, which is x squared. And we're going to get x squared minus 2x minus 8. Two numbers that multiply to 8, negative 8, but add to negative 2. I think that's going to be minus 4 and plus 2. Okay, so the 0, again, when we see an x by itself, not adding or subtracting anything, the 0 itself will be 0. That means it's going to cross through the origin. And the multiplicity on that is 2, right, which is even. So the effect on the graph is that it's going to touch at that point, but not cross over the x-axis. Okay, the next factor is x minus 4. That will be 0 if x is 4. The multiplicity is 1. It's used one time, which is odd, and therefore it's going to cross. Okay, so all we do is we look at the multiplicity, and again, this one's also used one time. We look at the multiplicity. The number itself isn't the big deal. It's whether or not it's even or odd. And then, again, our last factor here, x plus 2, that's going to be 0 if x is negative 2. The multiplicity is 1, which is odd. And so it's going to cross the x-axis at that point. Okay, now a polynomial function has a 0 at negative 6. So here's something we're working backwards here. We know that it has a 0 at negative 6 with a multiplicity of 2 and a 0 at 2 with a multiplicity of 1. And we're told to write a polynomial function in standard form that could represent this function. Well, let's start with factored form, okay, because we know what the zeros are. So if it has a 0 at negative 6, then one of the factors must be x plus 6, because if x was negative 6, it would equal 0. So if the 0 is negative 6, it means the factor is x plus 6. And the multiplicity was 2, so that's squared. Another one is x, okay, so x minus 2, right? That's gonna, if the 0 is 2, then when x is 2, this would be 0. When x is negative 6, this would be 0. So again, we're kind of using the opposite sign here. And the multiplicity is 1. Okay, so this is our function in factored form. Okay, that's our basic function. And so it's asked for standard form. Let's go ahead and multiply this out. Okay, first let's do x plus 6 times x plus 6. Let's just see what that is. That's going to be x squared plus 6x and plus 6x, and then plus 6 squared, which is 36. And so we're going to get x squared plus 12x plus 36. Okay, so that's what this equals. So let's write that in here. X squared plus 12x plus 36. And we're going to multiply that by x minus 2. Now, in the last couple weeks, we've learned different methods for doing this. I'm going to go ahead and just do the box method over here where I have a little space. So I'm going to have my x and I'm going to have my minus 2. And I have x squared plus 12x and then plus 36. I'm just going to multiply through here. So each cell is the product of the numbers at the beginning of the row and the column. Okay, so it looks like this is going to equal x cubed. I've got minus 2x squared and plus 12x squared for plus 10x squared, minus 24x plus 36x looks like a plus 12x, and then minus 72. All right. So that's our function in standard form. And key thing to notice, it says a polynomial function that could represent it. It could represent it because actually there's a lot of possible values. There's a lot of possible functions that could go through those particular zeros. And we'll talk about that a little bit more when we're in class. We'll do a little Desmos demonstration on that. Okay, that concludes the notes for this topic.